we have two machines here. So what is the probability or fraction of the time machine 1 is doing nothing, right? So machine 1 will be free if there's no parts there. And if there's one part, then there's a 50% chance the part will go to machine 2. And then machine 1 will still be free, right? So if there's one part, there's a 50% chance the part will go to machine 2 and machine 1 will still be free. And so therefore we will take 0.5 times the probability that there's one part there, right? So this is basically 50% chance machine 1 not get the part. So we know P0 is 1, 1, 1, 1, but we need to calculate P1. Right? Okay, we need to calculate P1. To calculate P1, there's a top formula and there's a bottom formula. And you use the top formula if n is less than k. And that is the case for us. So since n is less than k, for us we're calculating P1, so n is 1. And k is equal to the two machines we have. And so we should be using the top formula. So using the top formula, we have Pn is equal to lambda over mu to the power of n over n factorial times P0. Okay, and so we calculate P1. So lambda over mu, so 80 over 50 to the power of 1 over 1 factorial. P0 is 1, 1, 1, 1. And so we get 0.176. So the probably work out to be 0.198. So basically, 19.8% of the time, machine 1 is free. Okay, it says, how about machine 2? What is the probability that machine 2 is free? Well, as you can see, we've got two machines here, right? So, what is the probability that machine 2 is doing nothing? Well, what would be your guess? The probability that machine 2 is free? Yes? same. What difference does it make, machine 1 or 2, right? So it will also be 0.198. At least one machine is idle. So what is the probability that at least one is free? Well, at least one is free if there's no parts there. And then at least one is free if there's one part there. And then if there's two parts, then at least one's not free. So basically it's P0 plus P1, so 1111, and then the 176, give me the 287. Well, I was looking at your assignment 4 in the decision tree, and I realized that maybe it was too easy. Anyways, I'll add some more branches next time. Okay, next we're going to look at some economic analysis of our waiting lines. So, for example, is it better to have individual lineups, or should we have the so-called Walmart mega cash counter, right? So you can compare performance measures like the 2, L, LQ, W, WQ. You can also compare some costs, operating costs, parts, workers, waiting costs, space needed, and so on. Right? So let's see how we can do this. An average of 24 customers per hour arrive at a small driver's licensing office, Poisson Distribution, waiting to renew their driver's license, update their vehicle registration sticker, and so on. At present, we have 3 clerks working in parallel. Customers waiting a single line for the first available clerk. The average time for a clerk to serve a customer is 4 minutes, exponentially distributed. Clerk earns $12 per hour, and the government assesses a waiting time cost of $20 for each hour that a customer waits in line. Okay? First of all, when a customer finally reaches the clerk, what is the probability it will take 25 seconds or more to complete service? Okay, so T here is time to complete service. And it is exponential distributed. And so we have from the first or second page the exponential distributed formula. Anybody sign up for Mesacala here? 1? Okay, 1's better than 0, I guess. Okay, so we want to calculate the probability that it will take 25 seconds or more. Since our formula is giving us t is less than something, so maybe it's better that we take 1 minus, so that we have the same form, right? So we have the same form. Okay, so 1 minus, so this is then 1 minus e to the minus mu but we don't know what mu is. And t is 25. Okay, so we don't know what mu is, but t is 25. Okay, so we will need to calculate the mu, the time it takes to the service, so-called service rate. And we're told that it takes 4 minutes to process a customer. And so the service rate, mu, is 50 customers per hour, so 60 divided by 4. However, we've got a little time unit here, right? Because this is by the hour, but over here is seconds, and so we need to put them into the same time unit. And so I will convert this 15 customer per hour into per second. So mu is 50 customer per hour equals 15 divided by 3600. So that gives me 0.04166 customer per second. Okay, so putting my 0.004166, so the probability works out to be 9011. Then it says the manager feels that if there are more than 4 customers arriving in a 15-minute time period, then the office would have some problems with space. So what is the chance that the office will run into this problem? So X is number of customers arriving. In a time period. And we know from before it is going to be Poisson distributed. And so there's my Poisson distribution formula. And in the formula, lambda is the so-called arrival rate. Okay, so lambda is the arrival rate. And in the problem is given as 24 customers per hour coming. And again, we have a bit of an issue with time unit here. We got hour here, and we got minute over here. So either we convert the minute to hour or the rate into minutes. And so I'm going to convert this into minutes. So 24 per hour equates to 6 customers per 15-minute time interval. Okay, 24 customers per hour equates to 6 customers per 15-minute time interval. So we want to calculate the probability that there are more than 4 coming. So this includes 5, 6, 7, 8, infinity. So more efficiently to calculate as x less than equal 1 minus x less than equal to 4. Okay, so this is then 1 minus, includes x being 0, x being 1, x being 4. And so we can put this x is 0, so that will be lambda. Lambda is 6, so 6 to the 0, e to the minus 6, 0 factorial. And then x is 1, so 6 to the 1, e to the minus 6, 1 factorial, and so on. Finally, 6 to the 4, e to the minus 6, 4 factorial. And I didn't really get a chance to work it out, but whatever. Okay, next. What is the expected cost per hour to operate this office? So our model here is the MM3 because we have K is equal to 3 clerks. Okay, so expected cost per hour includes the cost of the clerk, so they get paid $12 an hour, and we times the 3 clerks. And then there's the cost of customer waiting, and the government assesses wait time of $20 for each hour a customer waits in line. So we will add $20 for each customer waiting in line. But then, how many customers are waiting in line? Well, that is basically just LQ, right? Okay, so that's $12 for each clerk times 3 clerks, and then every hour is $20. Well, how for each customer? How many customers in line? That's LQ. So we have our MM3 model here. So we have to get LQ, and we know the formula here, but it requires us to calculate P0. So rather than using the formula, maybe we could use the table to get P0, and then we could calculate LQ. So lambda in the problem is 24 customers are coming. And already we know from part A, the service rate is equal to 15 customer per hour from part A. Okay, so the ratio of lambda over mu is 24 over 15, and that's 1.6. And it's the same 1.6, so we know it's on the table, so that's good. Okay, so there's the ratio 1.6, but now instead of having 2 channels, we have 3 clerks, 3 channels. So P0 is 1872. Okay, so P0 is 1872. So that helps us a lot. And now all we have to do is use it and calculate LQ. So we will use it and calculate LQ. Okay, so LQ is lambda over mu to the power of k, lambda times mu, and then k minus 1 factorial, and then k mu minus lambda square, and times P0. Okay, we get 0.313. Okay, so now we know we got 36 plus 20.313. So the cost is 42.26. What is the probability you will not have to wait in line when you come to this office? Well, there's 3 clerks, so if there's no customers there, you don't wait. There's 1 customer there, you don't wait. There's 2 customers there, you don't wait. And then if there's 3, you wait. So probably no wait is basically P0 plus 1 plus 2. P0 we already have, 1872. But the other ones we have to calculate. Again, there's a top formula and a bottom formula. And for us, n is going to be 1 and 2, and that's going to be less than k is 3, so we'll be using the top formula again. So since n is less than k and n is 1 and 2, k is 3, once again, we use the top formula for Pn. Okay, that being the case, so we have to calculate P1, so lambda over mu to the power of 1 over 1 factorial times P0. And then P2 will be lambda over mu to the power of 2 over 2 factorial times P0. Okay, so now we add the two together. And so the probability is 7263. Now, we could have done it another way. So there was the formula here to calculate the probability a customer arriving has to wait. And so the probability of not have to wait is just 1 minus this PW here. So again, probably no wait is then 1 minus the probability you have to wait. And from the formula, the probability you have to wait is lambda over mu to the power of k over k factorial. And then we have k mu divided by k mu minus lambda. And then finally times P0. And you'll get the same 7263 back. Okay, so either way is fine. And then the final part, and the longest part, the government is considering replacing one of the clerks with a automatic service machine, or ASM. Management estimates of the 24 customers per hour that arrive, 20% of them will go and use the ASM. Customers form a separate line at the ASM and assume that customers are not permitted to change lines. An ASM takes an average of 8 minutes exponential distributed to serve each customer. It costs $5 per hour to operate the ASM. Should the government install the ASM? Okay, so the total expected cost per hour consists of the ASM system expected cost per hour. And now you have to add the cost of running the 2-clerk system and not 3-clerk. Expected cost per hour. Okay, so the total includes the ASM cost, and then you have your 2-clerk system cost. So we will calculate these separately. So let's start start with the ASM here. So customers come to the ASM, and there's only one machine, and out they go. So our model is back to the simple MM1, one worker. First come, first serve, infinite. Okay, so our model is back to the simple one server. So let me take out the formula for that one. Okay, so the arrival rate. Originally, we had 24 customers coming, but according to this, 20% of them will now go use the ASM. So the arrival rate to the ASM is 4.8 customers per hour. For the ASM, it takes 8 minutes to process a customer. And so the service rate is, it can do 7.5 customers per hour. Okay, then the expected cost per hour. The ASM costs $5 per hour to operate. So that's the ASM cost. And once again, customers waiting in line is $20. And then how many customers in line? That's LQ, right? So that, because it's the simple model, the LQ is easy to calculate, right? Given over here, the single server model LQ formula. So LQ is lambda square, mu and mu minus lambda. So we put in our numbers. Okay, so we plug in our 1.1378, and this cost will work out to be $27.67. And so now we know this one is $27.67. Okay, now we're going to calculate the cost of the two-clerk system. So the model then is my MM2. Okay. Then we calculate our arrival rate. So the 24, 20% is going to the ASM, so 80% is coming to the 2 clerk. So the arrival rate is going to be 19.2 customers per hour coming. And then the service rate, we know from part A, is 15 customers per hour. Again, we have to calculate the expected cost per hour. And so we have $12 for each clerk, and now we only have 2 of them. And then again, customer waiting is $20. How many waiting? Well, that's LQ, right? So we have to calculate LQ. And once again, to calculate the LQ, we need the P0. So again, let's see if we can look up the value of P0 on the table and then use it to calculate our LQ. So we calculate the ratio of lambda over mu. And we get 1.28. Okay, 1.28 is not on the table. So what does that mean? It means back to the formula. Okay, it means back to the formula. So cannot use table 11.4. So we have to go back and use our formula. Okay, so back to the formula we go. So 1 over. Again, sum of n equals 0 to k minus 1. K for us is 2 now, 2 clerks. And then lambda over mu. And then we have lambda over mu to the k over k factorial. And then we have k mu divided by k mu minus lambda. So this will work out to be 2195. I always find that after the Mesa Gala, I feel like I need to go eat some more dinner. So my suggestion is you should maybe eat a little dinner before you go to the Mesa Gala. Okay? Either that or you hope the people you're sitting at your table don't like bread And so, you can eat a couple of pieces of bread, you'll be fine. Okay, now that we have T0, we'll use it to find LQ. So lambda over mu to the power of k. Lambda times mu. And then k minus 1. And then k mu minus lambda. And then times T0. Okay, so we put it into the LQ over here. And so the cost will work out to be 41.76. Okay, so now we update our cost formula up here. So this is 41.76. So totally, it's going to be 69.52. So is it cheaper or more expensive? Well, from part B, when we had the 3 clerks, the expected cost is only 42.26. So this 69 is definitely a lot more money than the 42.26, and so we should not install the ASM. So since 69.52 is greater than the 42.26, and this was the 3 clerk, so therefore don't get ASM. Okay, so let me just walk you through the duration of the MM1 model here. Okay, so we're going to derive some of the formulas for a basic one server model. So that's the easiest one to do. So we begin drawing some so-called state diagrams. So this is state 0, so no customer in the store, 1 customer in the store, 2 customers in the store. Okay. You go from nobody in the store to become 1 customer in the store at the rate lambda, because that's how fast customers are coming. You go from being 1 to 2 at the rate lambda, because that's how fast customers are coming. You go from 2 customers in the store to become 1 at the rate mu, because that's how fast your workers are working, right? Then we write balanced equation to determine P0. It says for any state 0, 1, 2, 3, the entering rate must be equal to the leaving rate in steady state, right? So this principle allows us to express balanced equation for each state n, and then we solve to get Pn. Right? So we look at state 0 here. Okay? How do you get into state 0? Well, it's mu times P1. Right? How do you leave state 0? Well, it's lambda times P0, right? And then again, for state 1, how do you get into state 1? There's two ways. It's lambda P0 plus mu times P2. Okay? How do you leave state 1? There's two ways. Mu times P1 and lambda times P1. Okay, so basically after a while you start to see some patterns, right? Then we rewrite in terms of P0. So you can see P1 is simply lambda over mu times P0. Over here we have P0, P2, P1. And we can substitute P1 with lambda over mu P0 and we get this. And then after a while you start to see a pattern. If the state is 2, then this would be 3 and it would be the power of 3. And so therefore if this is n minus 1, then this would be n and it would be to the power of n. And this is where we get the Pn formula. Okay? This is how we get the Pn formula. Total probability adds up to 1. So that means P0 plus P1, 2, etc. has to be 1. We replace Pn with this here. And so P0 is 1 over this sum. And if this ratio or fraction is less than 1, you might recall from your finite math or whatever they call it these days, that this infinite series or sum has a closed form. And for us, this has to be a fraction because it's required by steady state. And so that's how we get our P0 formula. Expected number of customers in the lineup is the number of customers in the line times the probability of having that number of customers. So if there's no customer in the line, there's nobody in the lineup if there's nobody there. There's nobody in the lineup if there's one person there because it just goes straight to the story. There would be one person in the lineup if there's 2 people there, 2 people line up if 3 people there. So we can sum this here. We can replace Pn with this. And we can replace the P0 with this. And once again, if this is a fraction, this thing has a closed form. And it can be shown, it reduces to this. So this is how we get the LQ formula. Okay? Basically, almost all the weighted line models, the formulas are developed in this fashion. Right? So I just want to give you kind of a rough sense how they come. And I think that's it. And don't forget your assignment 4 is due. Any question on the assignment 4 there? Any question on the assignment 4 there? No? Okay.